Hello, student. My name is Wanda Ronald. I'm your teacher for physics. Today we are going to look at scientific notation and significant figures in measurements. Remember, in Form 1, we are looking at measurements in our second topic of physics after the introduction. In measurements, we looked at many things. Just to have a recap, we looked at length, measurement of length, measurement of mass, measurement of volume, and measurement of time. We looked at the units of those physical quantities, the SI units, and also how to convert these units to other units, or from SI units to other units of each of those physical quantities. But now, today, we look at scientific notation and significant figures in measurements. And the importance of this, how do you record what you have measured? Recording of what you measured, or noting it down with a certain number of significant figures or in a scientific form, is what we're going to study today. I need your attention. I need you to be very attentive, because in physics we do a lot of measurements that need to be recorded, and especially when you are in the physics lab doing the practicals, you are going to make recordings or writing down what you have measured, and you will be required to write them down with a specific number of significant figures or decimal places. And it is in this topic here, and this subtopic here, that you're going to understand how to write down the number of significant figures and also how to round off. Just to remind you, I know you studied this at primary level, but we did not go deep into significant figures. But rounding off is something that you're well aware, I believe. Okay. Now, scientists make measurements in their scientific experimental work. Now, when you go to the market, most of the items you buy are measured. Definitely, when you go to a shop, you want sugar, you measure the quantity that you want, and it has to be measured. It is important that these measurements are accurate. So when you have asked something to be measured, or when you are asked to measure something, you therefore require to note or record with accuracy. The accuracy of the measurement depends on two things. One, the number of significant figures, SF, and two, the number of decimal places recorded or used. The number of significant figures, and the number of decimal places. Let me just give you an example of values recorded, or a figure recorded down. Okay. It was stated in a newspaper that the attendance of fans at Namboole National Sports Ground for a football match was 24,000. Well, the records from the management show that the crowd was 24,492. Now, information from both sources are correct, but it was given to a different degree of accuracy. The newspaper recorded 24,000 fans, but the exact number recorded by the management of the sports ground showed that actually the number was 24,492. Now, as I've told you, this information is both correct, but the degree of accuracy is different. 24,492 might have been the exact number. When we round off 24,492 to two significant figures, it is 24,000. So the newspaper rounded off to two significant figures. Okay? But the management recorded the exact number which was in the sports ground. But doesn't mean that the newspaper was wrong. Okay? It's only that it was not very accurate. So the degree of accuracy was not the same. And for that case, you're going to understand how you can record values or measurements accurately using significant figures or the number of decimal places in this lesson. Please pay attention. Now, what is a significant figure? A significant figure is a digit that carries a meaningful contribution to a measurement. A digit that carries a meaningful contribution to the measurement. Let's take an example. 0.5 has one significant figure, while 50 has two significant figures. Now, when you look at 0.5, the zero before here has no significant value in this figure here. It does not have a significant value. But 5 is the one which has the significant value. And therefore, we take 5. However, when you look at 50, two significant figures. 50 has a significant value because when you remove it, when you withdraw this 0 here, when you remove the 0, it will remain 5 and it will completely change the value of the number. But here, when you remove 0, the value of the number still remains 5. Okay? But here, it will change from 50 to 5. So the 0 is significant in the value or in the number of 50. Now, the accuracy of the answer will depend on the number of significant figures. The answer will be more accurate. The answer will be more accurate if it is given to a higher number of significant figures. A higher number of significant figures. For example, if the other example we looked at, 24,492. Now, this has 5 significant figures. 5 significant figures. But this 24,490 has 4 significant figures. Likewise, this value here has 3 significant figures, and this one has 2 significant figures. So the higher the number of significant figures, the more accurate it is, or it becomes. Decimal places, others call them decimal points. Decimal places are fractional places of a number. Well, the other one is a digit which carries a meaningful. This one is a fractional place. A fractional place of a number. For example, 6.42 has 2 fractional place values or 2 decimal place values. You count the number, the digits. You do count the digits after the decimal point, which is 1 and 2. So this one has 2 decimal places, and this 4 2 4 2 is these are the fractional values, of this number. Decimal place is also the position of a digit to the right of a decimal point. I've already mentioned that. This position, these values here, or these 4 and 2 values, are the fractional places or the decimal places. A time of 5.50 hours has 2 decimal places. 5 is the first, and 0 the second decimal figure. That is obvious. Again, a value is more accurate, like we looked at with significant figures. Like I mentioned, a value is more accurate if given to a higher number of decimal places. So the more increase the number of decimal places, the more accurate it is. Again, also looking at this example, 4.562 has 3 decimal places, but it can be rounded off to 2 decimal places and 1 decimal place. We can get 4.56, that is 2 decimal places, or 4.6, which is 1 decimal place. Now when you look at these two values rounded off to 2 decimal places and 1 decimal place, and you look at the value which had 3 decimal places, there is a number which has been ignored. There's a number which has been left out, or numbers left out, making these rounded off values to a lesser decimal places less accurate. So also the higher the number of decimal places, the more accurate the value is. Okay, how about rounding off? Rounding off means writing a number to a required place value. Routing the number to a required place value. You can round off to a certain number of significant figures, or you can round off to a certain number of decimal places. Now the result is less accurate but easier to use. Less accurate. So the more you round off and eliminate other figures from the exact figure, the result becomes less accurate, but it becomes more easier to write or to use. For example, 7.52 centimeters to 1 decimal place is 7.5 centimeters. Okay, 7.5 centimeters. So this one, the two may seem not to have a significant value, but it tells you that actually this was a millimeter value, or a smaller value, but still it has been eliminated, so making 7.5 less accurate. So my dear student, having looked at what significant values are, significant figures are, decimal places are, and now we have known how to round off, which this was a recap, but just remind you, we are now going to look in more detail. Be very attentive here on the rules for significant figures. How do you identify significant figures? Rule number 1: all non-zero numbers or digits are significant. All non-zero digits are significant. Now the number 33.2 has 3 significant figures because all the digits present are non-zero. The digits present are non-zero. They are not zero, in other words. And therefore, this value here, 34525 meters, has 5 significant figures. So that is rule number 1. Know that a number which is not zero, a non-zero digit, is significant. Rule number 2. Zeros between non-zero digits are significant. Oh my God. Zeros between non-zero digits are significant. So a mass of 2052 kilograms has 4 significant figures. Now this zero here is between 2 and 5, and because it is between the non-zero digits, then it is also significant. It is significant. Example, area of 24014 meters squared has 5. Again, 0 is between 2 and 1. Now, rule number 3. Leading zeros. What are leading zeros? Zeros, the right of a decimal point and left of the non-zero, are not significant. To the right of a decimal point and left of the non-zero are not significant. Okay, so we have here, they are nothing more than just placeholders. The area of 0.54. Now this 0 to the left of the decimal point, on the left is this side, and the right of the non-zero, this is 5, which is a not 0. This 0 is not significant. Likewise, so this value here has 2 significant figures. When you look at this, this is these zeros here are also not significant. They are to the left of a non-zero digit. Okay, to the left of the non-zero digit, and these zeros are not significant. So even this value here has 2 significant figures. Rule number 4. Trailing zeros. Trailing zeros. The other ones we talked about were the leading zeros, which are to the left of the decimal place. Okay, to the left of a decimal place, rather, to the right of a decimal place, but to the left of the non-zero. Now, trailing zeros, all zeros to the right of a non-zero digit in the decimal part. Okay, trailing zeros to the right of a decimal place and significant. Let's take this very serious. Trailing zeros to the right of the decimal point are significant. All zeros right of a non-zero digit in the decimal part, that means those are trailing zeros. Okay, those are trailing zeros. Are what? Significant. A volume of 92.00 centimeters cubed has 4. Now these zeros are to the right of this non-zero digit, even after the decimal point. These zeros are to the right of the non-zero digit, and they are significant. And the height of 6.40 meters has 3. They are to the right of this decimal point and a non-zero digit. all zeros right over non-zero digit in the decimal part, remember, are significant. Okay. Now, 92.00 is different from 92. How? A scientist who measures 92.00 centimeters cubed knows his value to the nearest 100. Meanwhile, his colleague who measured 92 centimeters cubed only knows his value to the nearest ones. That is why these zeros are significant. It is important to understand that a zero does not mean nothing. Most of us think that the zero simply means it is nothing. Now, zero denotes or simply gives us the actual information, just like any other number. Okay? The actual information, just like any other. You cannot tag a zero or zeros that aren't certain to belong there. So these zero values here have a meaning, and therefore they are significant. Have meaningful values, and therefore they are significant. So zeros, all zeros right over non-zero digit in the decimal place are significant. I need you to understand these rules because you are going to apply them when you are recording or identifying significant figures. Number 5. Trailing zeros in a whole number with a decimal place shown are significant. Trailing zeros in a whole number with a decimal point shown are significant. What do I mean? Place a decimal at the end of a number is usually not done. Placing a decimal at the end of a number is usually not done. By convention, however, this decimal indicates a significant zero. For example, you can write a value like this: 540, then you put a decimal, or you might think you've put a full stop. That putting a decimal indicates that the trailing zero is significant. It means the trailing zero is significant. The number which is coming after these 4 is what? Significant. To the right of the non-zero digit is what? Significant. Okay. There are therefore now 3 significant figures in this value. But if this point here was not there, then this value would have had 2 significant figures. It would have had 2 significant figures. But because you put there this dot, okay, as long as you put it there, makes this zero significant. 6. Trailing zeros in a whole number without decimal point are not significant. Without a decimal point, writing just 540, if you don't put a point something or point, indicates that the zero is not significant. I'd already talked about that. The zero is not significant. So therefore, if you are not required, don't put it there, point. But if you are, then you put it there to give the zero a significant meaning. So writing just 540 indicates that the zero is not significant, and therefore there are only 2 significant figures in this value. Okay, this value here is rounded off to 4 significant figures. and this one has 5 significant figures. Okay, the zeros are between non-zero digits 1 and 3. So by rule number 2, since they are between the non-zero digits, they are significant. Okay, these zeros here 1, 2, 3, now they are between the non-zero digits, they are significant. We need to drop the final 3. We want to round this off to 4 significant figures, and therefore it has 5. Okay, it has 5. So how do we round this off to 4 significant figures? Now we say we need to drop the final 3, since 3 less than 5. Okay, now we leave the last 0 alone. Now if therefore we write 1 0 0 0 and we put there point, we put there this point, then this value will have 4 significant figures from the rule number 5 and number 6. We see that in order for the trailing 0 to count as significant, they must be followed by a decimal point. They must be followed by a decimal point. So here we're trying to round off this value which has 5 significant figures. Why 5? Because these zeros are between the non-zero digits according to a rule we mentioned above. But again, to round it off to 4 decimal points, if we just wrote 1000 like this, 1000 like this value, it will have 1 significant figure. These zeros would not be significant. So to make them significant, we go to our rule number 5. And rule number 5, just place a decimal point and make these zeros significant. So 1 0 0 0 point has 4 significant figures. So this is an example to illustrate rule number 5 and rule number 6. I repeat, this value of 1000.3 has 5 significant figures, but we need to round it off to 4 significant figures. Now rounding it off to 4 significant figures, if we drop the 3 without placing there the decimal point, the value will be 1000, which has just 1 significant figure. But the moment we place there this decimal point, it makes these zeros significant, and therefore the value will now have 4 significant figures. I hope you have understood that. The last rule is very much attention, because this one here is going to teach us something different. For a number in the scientific notation, n times 10 to power x or to power some value, all the digits comprising n are significant by the first 6 rules. 10 and x are not significant. So these values are significant, but these 10 and x are not significant. An example, 6.02 times 10 to power 4 has 3 significant figures. These values here, we shall use the first rules on how to get the significant values. For example, this one is between the non-zero digits, so this value is significant. Okay, but this 10 to power 4, the 10 and the 4 are not significant, so this value has significant, 3 significant figures. Now, this rule gives us an opportunity to change the number of significant figures in a value by manipulating its form. Manipulating its form of how to write it. You can write it in scientific notation and you change the number of significant figures. For example, let's try writing 1100 with 3 significant figures. Of course, from the rules above, this value here has 2 significant figures, only 1 and 1. But we want to change it to 3 significant figures. Okay, 3 significant figures. So by rule number 6, this has 2 values, so its trailing zeros are not significant. They are not significant. So if we add a decimal, at the end, we shall make it 4. Remember with our rule number 7 and 6. So if we add a point here, we make this 0 significant, and that will have 4 significant. But by writing it in the scientific form or in the scientific notation, okay, 1.10, 1.10, this value here will have created now 3 significant value. This value here, that this number here which comes before times 10 to power x will be what? Significant. So this is a significant, these values all have the significant value, and therefore this has 3 significant figures. 3 significant figures. Okay, I repeat, this value here has 2 significant figures, the one I'm pointing at here. No, the one without a decimal point. This value here has 2. The moment you place a decimal point at the end, you make it to have 4. But if you want to change it to have 3 significant values, then you can write 1.10 times 10 to power 3. Now this whole value here will take the n value in this notation, and this n value, all the digits comprising in the n are significant. So all these are significant, and we shall have this value to be having 3 significant figures. Okay, now you are going to do the exercise on practicing those rules of significant values, and you see how you can identify them. But let us first go to the rules of rounding off before we look at examples, because we are going to be rounding off to see the specific number of significant figures or specific number of decimal places or decimal values. Rule number 1 for this: if the digit to be dropped is less than 5, if the digit to be dropped is less than 5, the preceding digit is left unchanged. Just to remind you, let's look at an example. Rounding off 4.264 meters to 3 significant figures. Now the answer, this one is the first one, the second, the third, because they are non-zero digits. Now that means that you are going to drop off the 4, but this 4 you have to check, is it less than 5 or 5 or greater than 5? Now you can see that the 4 is less than 5, and if it is less than 5, the one you are going to drop to make it to 3 significant figures here, we are going to drop the 4, and the 4 is less than 5. Now if the 4 is less than 5, then the value that comes before the 4 is left unchanged, which we are calling the preceding value coming before this value is left unchanged. If you didn't know that, I think now you've known that it is not changed, and therefore here just drop off the 4 and say 4.26 meters. Now this value has 3 significant figures. Another example, rounding off 5.62 centimeters to 1 decimal place. Because we want only 1 decimal place, we shall need the 6. But we look at the next value, which is 2. Is it 5? Is it greater than 5? Is it less than 5? Now, since the value after the 6 is less than 5, then we just drop it off and leave the 6 unchanged, and we have 5.6 centimeters. That is using that rule. Now how about if the digit to be dropped is 5 or greater than 5? The preceding digit is raised by 1. Yes, the preceding the digit that comes before the value to drop is raised by 1. An example here, let's look at rounding off again this value here, 4.265 to 3 significant figures. Now this is 1, 2, 3. We need to stop here. The value after the 6 is to be dropped, but because it is 5, or if it is greater than 5, then this preceding value is raised by 1. Is raised, you add the 1 to the value before, and this value becomes 7. So therefore we shall write 4.27, not 6. We write 4.27 meters. So therefore this one, rounding off to 3 significant figures, is 4.27. Good. How about 4.268? This 8 now is greater than 5. Since it is greater, then you also raise this 6 by 1. We also get 4.27. Okay, 4.27. But up here it was less than 5. These values are less than 5, so this value remains unchanged. Using rule number 1. Rule number 2, this value is raised by 1 if the after value is 5 or greater than 5. Okay, rounding off 5.6263 grams to 2 decimal places. Again, we look at 2 decimal places, 1, 2. The value next is 6. This 6 is greater than 5, so therefore we raise, since the 6 is greater than 5, we raise this value by 1, and we get 5.63 grams. Hope that is how we shall be rounding off. I want you to note also that when multiplying or dividing numbers with different significant figures, the answer takes the lower number of the significant values, the lower number. I'm going to explain this in this example. Okay, evaluate the following numbers. Now, I want to say 4.68 times 2.3. Now this first value has 3 significant figures, and this second value has 2 significant figures. Okay, now this is quite different. Let's look at this value. There's a mistake here. 4.684 times 6.31. Now this 4.684 has 4 significant figures, while this one has 3 significant figures. So when I multiply and I get this answer 29.55604, to how many significant figures do I write? Because this one has 3 and this one has 4, I write to the one with the lowest number of significant figures. To write the one to the lowest number of significant figures, and rounding off, we shall have to write to 3 significant figures, and the value now will be 29.6. Please ignore this example up. Let us use this one here. I think there was a mis typing there. So when we use this one here, to follow this rule here with multiplication, this has 4 significant figures, this has 3. The number has to be rounded off, the answer has to be rounded off to the 1 to 3 significant, to the lowest number of significant figures. Okay, let's look at division. Again, in our division, we have 68.4 divided by 8.4. The 68 has 68.4 has 3 significant figures. 8.4 has 2 significant figures. So when you divide, if you press your calculator, you can try it out, you get this answer here, which is not rounded off, 8.142857. Now, how many significant figures do we write? Not decimal places. They both have the same decimal places. You can see 1, even here 1, but the number of significant figures are different. This one has 3 and this one has 2. So we shall round off to the 2 significant figures, the one with the lowest. We shall take the lowest number. So we shall need to round off this to 2 significant figures. So this value should be rounded off to 2 significant figures. So when we divide, instead of writing completely like this, we shall just have to write 8.1, because again, when you look at this one, is 4, which is less than 5. So we shall just drop all these others and leave this as 8.1. So remember that, look at the number, which one has which one takes the lowest, you round off the final answer with the number with the lowest number of significant figures. Okay, for multiplication and for division. So this 68.4 has 3 significant figures, 8.4 has 2 significant figures. Because we have the 2, the final answer will take the lowest. So we shall round off this one to 2 significant figures, giving us 8.1 as the final answer. How about adding or subtracting? When adding or subtracting numbers with different number of decimal places, the answer takes the lower number of decimal place. Examples: 46.845 plus 45.3. This value has how many? It has 3 decimal places, while this one has 3 decimal places, while this one has 1 decimal place. So we shall write the final answer to 1 decimal place. We take the lower one to 1 decimal place, getting 92.1. Round off to 1 decimal place. Subtracting also, excuse me, this one has 3 and the other one has it has 1 decimal place, not 2. It has 1 decimal place, and therefore the final answer will be to 1 decimal place, because this one has 1 decimal place, not 2. This one, there's a mistake here. There's 1 decimal place, so even this one will be 1 decimal place. Now, those who have enrolled for the program, those who are enrolled, who have enrolled for PECO, will be given an exercise to try out, or they will receive the exercise to try out these numbers of writing significant figures and rounding off to a specific number of significant figures, to try to practice. But I want also to encourage you to write the notes so that you can revise without just watching. You can also revise later those rules of rounding off and rules of significant figures and be able to write them correctly. So when you are given the exercise, you will do it, and I will go through it to see what you have understood or whether you've understood. We talked about scientific notation, or the standard notation form that we need to write numbers. Now, scientific notation or standard notation is a short and a more convenient way of expressing very large or very small, very large or very small numbers using the power of 10. It is also called exponential notation. Okay, let's take an example. The distance between the Earth and the Sun is 153 million kilometers. Now, writing all these digits can be simplified by writing 1.53 times 10 to the power 8. And how do you write it? You count. You say 1, 2, 3, 4, 5, 6, 7, 8, 9. So you put a point here and you count the rest. 1 point. What are the remaining? 1, 2, 3, 4, 5, 6, 7, 8. So you say 1.53 times 10 to the power 8, which is the scientific notation. Another example, the mass of the Earth. Mass of the Earth, it is 5972200 and all these zeros. How can this be written? How can this? Oh, how can it be even read? You can practice. How can it be read? Because if we have how many zeros? 1, 2, 3. These are 9. These are billions. These are 12. These are trillions. These are 15. What are these? These are 18. These are 21. Okay. These are 24 zeros. 24. How do you read that? Or how do you write it? So we just simplify this number, or the mass of the Earth. We can just write it in the standard form and say, okay, 5.9722 5.9722 times 10 to power how many? We count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So times 10 to the power 24. Now this is an easier way of writing this number, this mass, than writing it, the whole of it. Temperature at the core of the Sun is about 15 million degrees Celsius. 15 million, which can be written as 1.5 times 10 power 7 very easily. So scientific notation is an easier way of writing very small or very large numbers. Let's look at the smaller ones. Like the mass of an electron. Mass of an electron is 9.1093, or we can round it 9.1 times 10 power negative 31. Now if you write all these zeros, it will be 31 zeros, even 31 zeros. So this is an easier way. Volume of the universe. 3.58 times 10 to the power 80. How do you write that? Eh? To even take the whole 2 lines in your book. So to simplify it better, you can write it in scientific form. So for the above measurements, it is more convenient to express them in scientific notation form. Okay, to express them in scientific notation form, as you can see. Okay, yeah. Now, senior ones, before we do much, there's something I've brought in that I want you to pay attention, that you may think it is light, you may take it lightly, but it is very serious on the use of a calculator when it comes to those scientific notations. Yes, the use of our scientific calculators. We need to understand how they work. Yes, you can multiply 4 times 6 and you get an answer, 24, so easily. But when it comes to typing in this scientific form, you need to have understood how you type them in. There is a button here which is times 10 to the power x, and there's a button in this calculator here which is exp. Now the exponential button, it is called the exponential button. Now this button help you to express your entries in scientific form in the calculator. So scientific calculators have button labeled exp or times 10 power x, used to type on the screen a figure in scientific notation. What appears on the screen when you express the exp, or when you press the exp button, is a letter E. Some calculators show a letter E. The E letter represents, it is a program to show that it is times 10 to power, times 10 to power, and followed by a power. So for example, when you get your scientific calculator, for example, when you type 6, the exp button and 4, so some calculators will show 6E4 will appear on the calculator. Then what does it mean? Now it means that you have typed, or you have entered 6 times 10 to the power 4 in the calculator. Now that's how the calculator understands it, that it is 6 times 10 to the power 4. 2e negative 3 means it is 2 times 10 power negative 3. But the other calculators, the exp is labeled times 10 to the power x. So when you press this button, pending the power, which substitutes the power box. So on the base 10 value, how the calculator screen appears with the scientific notation. Now there we have been looking at how you enter it, but it also gives you a value which is in scientific notation. If the number is very big, it can give you an answer already given in scientific notation. How do you understand that? Okay, for example, that one there, so it is 8.9785901, but there is times 10, this value is 10 to the power negative 01. This simply means it is this value times 10 to the power negative 1. This value times 10 to the power negative 1, which appears on that calculator. I hope you have understood the scientific notation on the calculator. You can practice on multiplying big numbers and you'll see what it appears. You can use scientific notations and you see what appears on the calculator. I left you to practice on that because you will do that more often with the numbers we shall meet later. So as I finalize, I want to look at the scientific method. The scientific method is a process of conducting experiments that is used to explore observations and answer questions in the society. Okay, to answer questions in the society. You have a problem, think about the problem to get the solution. That is the scientific method. So physics depends on the practice of making observations. You observe and then carry out experiments. Observe and carry out what? Experiment. Okay, so in science we observe. After you have observed, what is happening? You raise the question. That means what is happening? What is the problem? Then you carry out experiment and make discoveries. Carry out experiment and you make discoveries. So this scientific method follows these steps below. Okay, the first step is the step of observation. If you are going to carry out an experiment, a discovery, you have observed. And after you have observed, what comes next? What do? You ask. For example, they say Newton saw an apple fall. The seeing an apple fall was an observation. So an apple fell. But then Newton, after observing that, had to ask a question. Okay? Why did the apple fall? What caused the apple fall? What caused it to fall? Okay? Then, after you have raised the question, see, what is that? What caused that? Then you formulate a theory. Your imagination. You think you have a solution to it. Okay? Maybe somebody hit it down. Okay? Maybe the tree shook. Those are theories. The tree shook and the apple fell. That's your theory. You think it is the answer to your question. Okay? So, after you have come up with a theory, a suggestion to the problem, trying to predict the reason as to why the apple fell, then you predict and then you experiment. Formulate theory and say, think it is because it is this answer. It's because the apple fell because it was hit down. Maybe there's something up there which shook the tree to make the apple to fall, and I think it fell. So you have I think somebody hit it down. So that is a prediction, but then you experiment. So after you experimenting, then you come up with a conclusion. A conclusion to show that you eliminate all the others. After carrying out the experiment, then you conclude and come out with one solution, and that is the procedure for the scientific method, for the scientific way of doing things. You don't just guess and say and conclude. No, you must experiment. You must experiment to prove that your answer is correct. Even when we shall be carrying out these experiments in physics, it is just to verify and also say, okay, Newton was right. In his laws of Newton, laws of motion, he was right. So you carry out experiment to prove, as we shall see later in physics, in most of these scientific experiments are just to verify, but they came up because of observation, because of asking questions. After you have observed, then people formulated theories and they predicted, but they did the experiments to verify whether their predictions are correct until they concluded. And that is the scientific way of doing solving problems. So the steps in the scientific method, as I conclude, one is make an observation. For example, a torch does not light. You have a torch and it's not lighting. You see, you will ask yourself, ask a question, why doesn't the torch light? Why isn't it lighting? So that is the question. Step number 2. Step number 3, form a theory or an explanation that you can test. For example, maybe the torch doesn't light because the bulb is blown, or the dry cells are not working. Okay, then predict what will happen, because based on the theory, predict. For example, a new bulb will make a torch light. So if your theory was that the bulb is blown, test. You just say, for example, if I put in a new bulb, it will work. Okay, then test the prediction through the experiment. Do it. Get the new bulb, put in the torch, and if it works, then it means that your prediction was correct. Remove the top and replace the bulb with a new one. Okay, replace the bulb with a new one. Then use the results to conclude, make a new theory. For example, the torch did not light because the bulb was blown, or it failed to light. Failure to light is not due to the what? Blown bulb. So if you put in a new bulb and still it does not light, so it means that the previous bulb was also not having a problem, it was not blown. And then you go further and look at another prediction. Maybe the dry cells are worn out. They are worn out. We replace, test. Then after that, get the conclusion. Then you come up with the solution. So in the second case, look for another theory to answer your question and test it. Repeat until you get the correct what? Answer. After putting in the torch, the new dry cells, and they have still not worked, think of another prediction. Continue testing until you come up with the correct theory or observation. So here I'm showing you a picture of observing through a microscope, which one of the methods used in scientific method. When we observe in science, we normally use 4 of our senses to notice things. We look at things when we use our sense of sight. You have to observe. Okay, we feel things when we use our sense of what? Touch. So I'm just reminding you about the 4 senses that are used. We listen to things when we use our sense of hearing. You have to listen. It is also important also to smell things when you use a sense of smell. The 4 senses: feeling by touching, seeing, feeling, hearing, and smelling. Those 4 senses are very important. We do not usually use a sense of taste, as that could be dangerous. Dear student, testing something, for example, if you're in a scientific lab, there is no need to put your tongue there to test. For example, a wire that you are testing whether current is passing, you will be shocked and we may lose you. So the sense of taste, be very careful. It's not always used in scientific experiments. This is very dangerous. But feeling, seeing, hearing, and smelling, that one we can use. So be very careful and never try testing things. Okay, let me see this chemical here. Your tongue will be burnt and will lose you. So be very careful with that. So now, in my activity, I want you to think of a problem, solve a problem using a scientific method. and solve a problem using a scientific method. So I want to ask you to maybe you may need a radio which does not work, but with all the dry cells inside. Now, a pair of new dry cells to test. What do? Copy the table below in your book. Use the guideline provided in step 1 up to 6, as we saw above, to carry out, to kind of come up with observation, ask the question, formulate a theory, and make a prediction. Carry out the experiment, by that is testing the prediction, and make what? A conclusion. It may not be a radio. Look at something at home which is not working and try to find a way of how you can make it work by finding the solution through this scientific method. Dear student, thank you very much for watching my tutorial and listening to me. I hope this will make you benefit. In our next lesson, we shall look at measurement of density, but it was very important to look at the scientific method, the way we record our things before we proceed. Please make sure you call those numbers. If you have acquired this tutorial, you can call those numbers to reach PECO Virtual School and see how you can acquire these tutorials to help you understand physics. We don't offer only physics, but all the other subjects, so you could benefit. Thank you very much for watching and listening to me. God bless you.